Hi everyone, we will present you with a reinforcement learning approach named Dreamer and our progress in improving it. Dreamer is an RL agent that learns visual control in its dreams. Dreamer learns two big things. First, it learns how the world behaves. It learns to emulate the world purely by itself, just like dreaming. Second, it learns how to behave in the world by acting in its own dreams. This solves two critical problems in RL, expensive environment interaction and noisy gradients. Dreamer follows the RL approach for visual control. An environment gives observation and rewards based on an agent's past actions, and an agent's goal is to learn an action policy that maximizes the sum of rewards. So I mentioned that Dreamer first learns how the world behaves and then learns how to behave in the world. This is the first part, where the actual goal is to learn the dynamics of the environment. For this, Dreamer uses a world model, a hybrid of RNN and VAE. So the three components of the world model are trained together to learn a predictive latent dynamics model of the environment. To help your understanding, let me show you this visualization. The video on the left shows the actual observation in the environment, and the video on the right shows the reconstructed images from the latent state of the world model. And some interesting things can happen if you recall that the transition model doesn't require observation. When we make transitions with learned dynamics solely, we can reconstruct the images without interacting with the environment, just like when we imagine or dream about the world. So this video shows how the agent dreams within its own world model. Without seeing the actual tracks, the agent dreams about the tracks and driving. And observe that during a dream, every model output is determined only by the world model's parameters without any unknown factors interfering from the environment. And from that, the gradient of any dreamed output can be analytically computed and backpropagated through many transitions. And recall that in traditional RL, the noisy gradient estimates make a problem. The world models gives us a solution because analytic gradients generally have low variance. And additionally, because the transition model gets latent state as input, we can safely discard reconstructions. We now have an extremely compressed world model with a small computation load because we don't use any images anymore. Now we can train a policy on top of it. To obtain stable gradients, training of the behavior model is done with dream trajectories only, without actual interaction with the environment. For doing that, Dreamer adopts an actor-critic approach that we skip for the interest of time. Now finally, we have all the components we need. After training, we can now deploy the RL agent in the actual environment. The results from the paper shows that Dreamers outperform previous methods overall in each continuous test like working, cutball, and so on. And at persistence prediction, the Dreamer shows robust performance. However, we can see some degree of degradation in some of the results, especially when the dreaming steps get larger. From the results, when we think about extending further model actions, which are more than 50 steps, future state estimation can likely be inconsistent. We refer to this problem as the long-term dependency problem. Dreamer used some kind of implicit techniques to facilitate long-term dependency, but we also suggest that Dreamer can benefit from explicit modeling of long-term dependency. In the NLP domain, the attention mechanism was the key to solve this kind of problem. So we decided to use attention to model LTD in Dreamer. Specifically, we were to use causal attention, where the model learns to recall past experience. So this is a normal RNN structure using the natural NLP models, and the structure is similar to the world model used in Dreamer. But in causal attention, when you look at the past state to generate current state, the attention provides arbitrary past skip connection, therefore facilitating long-term dependency. And finally, we expected two key challenges in applying the attention to the Dreamer. But to make the problem easy, we initially decided the reward model as the modification target.
Let's start with the replication progress. As we mentioned earlier, the specification we used are these. The difference between the original paper here is that we implemented not a TensorFlow version, but PyTorch version. And we replicate the walk-around model among the various models used in the Dreamer. To compare with the original Dreamer performances, we went through 1000 learning episodes processes. This is the graph of training rewards results. The above graph is the original PyTorch version learning reward value of the Dreamer, and the below graph is the learning reward value that we implemented. As you can see, it has almost the same graph results. Next is the test rewards for both paper and our application. For above graph, Dreamer PyTorch version is dark blue. Comparing two graphs, early episode seems to have low similarity, but as it goes to the end of the episode step, both graphs converge to same 1000, which means as episodes number getting higher, test rewards gets better. So let's look at the simulation of replication. The first picture represents early test episode, and the second picture represents late test episode. As the episodes get longer, episode 1000, which has done more learning, shows better test results. When we compare our replication to original Waka, it seems to be slightly different. But let's look at the reason why.
So why is it different from original implementation in Dreamer replication? Even the result in same kinds of code and framework, writing code is kind of heuristic work, so the result can be different. Also, TensorFlow and PyTorch offer different structure and functions module to do even same task, so the calculations in deep learning model can be different. Next, we show what we will do next. As we explained before, to enhance the performance of the model, we will attach casual attention to RNN of Dreamer. Especially, we can consider reward model for the modification. Then, what estimation would be helpful? Dreamer predicts states based on Markov assumption, but our hypothesis is that it is not really good assumption for predicting for the states. Then how do we prove the hypothesis? We can simply compare the episode return between previous model and our method in imagination horizon longer than paper experiment 1 over 40. We can show the result in both quantitative and qualitative aspects. We also compare the weight between connections to the reward model. Different with previous method, we can see dependencies also same weight from the past state. This is our progress presentation. Thank you for your attention.